Hi! So you want to know more about machine code and speak the native language of computers. Oh, not the ones and zeros which are ridiculously painful to read, but something more human-readable, like assembly. Here's a quick guide to how it works. The first thing to note is that there are different variants of assembly. This is because not all CPUs are the same. The instructions available that a CPU can execute may vary, depending on something known as the Instruction Set Architecture, or ISA. Think of an ISA as a manual of all permitted machine code the CPU can understand. There are many types of these manuals to choose from. Each CPU interprets machine code using one ISA. x86 and RISC-V are examples of ISAs, but in this video, we'll be just using RISC-V. Despite the variance in ISAs, machine code takes on a general form. It starts with the instruction type and is typically followed by 1 to 3 arguments. An example of an instruction is add RD, RS1, RS2. So this is an add instruction that takes the value in one CPU register, RS1, adds it with the value in another CPU register, RS2, and stores the answer in register RD. The register names in the instruction are actually acronyms. RD stands for Destination Register, while RS stands for Source Register. You can imagine registers as just temporary storage bins in the CPU for data. In the add instruction we had, for example, the CPU was essentially fetching values from the storage bins, performing computation, and then storing in another storage bin. There are what I like to call a few broad categories of operations: arithmetic, logic, memory, which consists of load and store, jump, and branch. Arithmetic instructions are ones where we perform mathematical operations. For example, we have add, shown previously, subtract, and negate. These instructions are examples of decompilation from these C instructions. We also have this very interesting looking instruction known as add-I. This stands for add immediate, which allows you to add a constant known as compile time of the assembly code. In this case, the constant 5 is added to RS1 and stored in RD. To subtract, we use the same add-I instruction but provide a negative value as the immediate. Logic operations, on the other hand, are bitwise logic operations. Remember those AND, OR, NOT, or XOR gates in digital electronics? You can do it here as well, with both the instructions dealing with purely registers and their variants involving immediates. There are also bitwise shift operations: shift left to multiply by 2, shift right to divide by 2. These operations are cool and all, but not all data is stored in the CPU registers. Some are stored in memory, which needs to be brought onto the CPU registers for operations to be performed on them. Load operations do just that. The LW instruction here stands for load word. A word is 32 bits in size, or 4 bytes. It has a very interesting syntax. The first argument is the destination register where the data will be loaded. The second argument is unique, taking an immediate and a source register surrounded by brackets. This means that the CPU will read the memory address in the source register, say location 5, and add to the address by the amount specified by the immediate, for example 3, which makes it 8. It then accesses the memory at location 8 to retrieve the data to be loaded into the destination register. There are also options to load data in smaller units, like LB, which is load byte. Then, we have the most basic load instruction, LI, which stands for load immediate. This is commonly used when we want to initialize a variable, for example, as it just loads a constant to a register. Sometimes there is not enough space to store results on the CPU registers, so the compiler might opt to spill them into memory. Hence, there's also a group of store instructions. The store word instruction also has a special syntax similar to the load instruction. However, the difference is that the first argument is the source register that contains data to be stored. This is followed by the second argument, which has the immediate and the destination register. For example, in this instruction, the CPU possesses data in the RS2 storage bin and wants to store it in memory. In this case, the CPU goes to read the address stored in RS1, say 0, and adds to the address by the amount specified by the immediate, which is 3, giving 3. Now we know that the data in RS2 needs to be stored at location 3 in memory. The CPU then takes that data from RS2 and stores it at the appropriate location. Now, at this point, let us integrate whatever we have learned so far with a real decompilation example. We have an add instruction acting on A1 and A0. Here, we are performing the addition of X and Z. Instead of storing the result into a separate register like A2, the compiler reuses A1 as an optimization. The next line of code translates to an add-I instruction since we have a constant 5 that we are adding to X. Finally, the two variables y and a are added together and returned. Now that we have seen how to translate mathematical operations and assignments, let's look at the more complicated things like if statements and functions. Branching allows us to do conditional skips on instructions, allowing us to do things like if statements. Here we have an if statement that checks if x is less than 5. If so, it increments the value of x by 100. Looking at the machine instructions, we see a peculiar load immediate instruction where 4 is loaded to register A5. This is followed by a branch greater than instruction, which compares the value in register A0 with A5, that is 4. A0 is variable x in this case. If A0 is larger than 4, we skip the next add-I instruction, branch to L2, and execute the return. Else, we proceed to execute the add-I instruction, which adds 100 to A0 before we execute the return instruction. But wait, there's no 4 in the C code anywhere, so where did it come from? On line 2 of our C code, we see that there is a x less than 5 condition. In RISC-V, we read the instructions sequentially line by line, without skipping any function blocks by default, unless there is a branch instruction. Hence, the decompiler inverted the original conditional interpretation, so that we skip the add-I instruction when x is more than 4. Beyond branching, we also have jump instructions. Jumps are unconditional skips, allowing us to perform tasks like calling a function or jumping to the return address. Compilers are the bread and butter of transforming the code that we write into low-level machine code that computers can understand. If you want to try to decompile some code for yourself, you can go to this website called godboard.org to play around. Thanks for watching and happy coding!